Hello, everyone. Welcome again to Python all day. We are still continuing with our journey on learning PyTorch. And I wanted to touch base on tensor operations because, as I said in my previous video, tensors are pretty much the bread and butter for machine learning and also for deep learning. So we'll be working with tensors pretty much as we build and train um, our models, and also as we make predictions with the models as well. So tensors is something that we're going to be able to see throughout the coding, and I just want us to continue to familiarize ourselves with tensors. And now I just want to talk about some basic operations with tensors like addition, subtraction, multiplication, and also division. Um, this little bit of tensors, as we saw in the previous video, we have the one-dimensional tensor, which is a vector or rank one tensor. We talked about scalar, which is rank 0, or which is a zero-dimensional tensor. It's just essentially a number. A scalar is just a whole number, like 1, 25, 30, 68. Those are scalars. Then we talked about a vector, which is a one-dimensional tensor. And then we also talked of a two-dimensional tensor, which we call a matrix, and it's also a rank 2 tensor. It's a matrix. It has rows. You see, this is a row, the horizontal row, and row. Then it also has columns. This is a column, and column. So this vector, or this two-dimensional tensor, the way we talked about size, we're talking about size. The size, we said, is the number of rows. We start with the rows. 1, 2, 3, 4. 4 rows. So it's a 4 by 1, 2, 3, 4, 5 columns. So this is a 4 by 5 a tensor. And it's a two-dimensional tensor. Rank 2 tensor, and that's a matrix. Then we have a three-dimensional tensor, which is rank 3 tensor, and it's more like you can think of it as a cube, and that's a three-dimensional tensor. It has depth as well, and that's a three-dimensional tensor or rank 3 tensor. It can either be like this or it can be like this, where you can see there is also depth here. There's this one, the top one, then there's another one here, then there's another one. So the top one is the matrix. It's actually the matrix that we had here, but there's another matrix behind it and another matrix behind it. That makes it a three-dimensional. That makes it a three-dimensional tensor. And this is another example of a four-dimensional tensor. Any tensor that is 3 dimensions or more, we call it higher order tensor, as we saw before. This is a 4-dimensional tensor. You have a 3-dimensional tensor, which is the cube, but then you have them stacked on top of each other, and that gives it depth. So that's a 4-dimensional tensor or rank 4 tensor. And then we have a 5-dimensional tensor, and on and on and on. So, but I want us to talk about basic tensor operations. And I wanted to talk about the sizes, because the sizes and the shapes, they are going to be able to affect, and we'll see that once especially we get to multiplying tensors. But the shape, size, those are very important concepts to be able to understand. and they're also very, very easy to understand. Once you get the hang of it, they are just very, very easy concepts to understand, but they're also very important because they're going to be recurring as we go through working with models and also learning on machine learning and deep learning. So I just wanted you to be aware that those are important concepts. The size, shape over tensor, very important. So we'll go next here and we'll talk about basic tensor operations. We'll talk about the arithmetic operations, which are addition, subtraction, multiplication, and division. I want to start with talking about addition. And as you can see here, tensor addition in PyTorch is primarily performed element wise, meaning one element wise at a time. This is one element in this tensor, and this is another element, this is another element, this is another element. So it's normally performed element wise. And what this means is that this means each element of one tensor is added to the corresponding element of the other tensor. Very important. Also very easy to understand. And for this to occur, both tensors must have the same shape. We say this is very important. Both tensors must have the same shape, or they should be broadcastable to a common shape. We'll see about broadcasting, but for now, just know that for you to be able to do element-wise addition, the tensors both tensors that you are adding should have the same shape, you know. And it's very easy to understand too, and it makes a lot of sense because if you add in a tensor, what you want to do is that you want to be able to add this, you want to be able to add this, you want to be able to add this, and you also want to be able to add this. So it makes a lot of sense that the shape of the tensor, of the two tensors, should be the same. Like I have this tensor here, tensor 1, and you can see this. Don't worry more about the torch.tensor. We'll talk about that as we go, but this tensor, just concentrate on this, the area within the square brackets. And when we look about, or rather within the parentheses, as we talk about the shape, this is how you can look at the shape. The shape, remember, we said it's rows and columns, rows and columns. So this tensor, it has one, see, this is one row, and this is another row here. So this is a two rows. So we have the two there. And then the columns, you can see each row has one, two, two columns. So this is a tensor of, it has two rows, because this is the inner square bracket here, and the closing inner square brackets, that's the first row. And also for the same year, this is the second row. So it has one row and comma, another row. How beautiful is that? It has one row, comma, then it has another row. So that's two rows. The shape is rows and columns. And then it has how many columns? It has one, two columns in each row. This row has one and two columns. See, one, two. And this other row has one, two columns. So it's two columns there. So this is a 2 by 2. And the other one, the same way, you can see it has one and comma, two rows, and then it has one and two columns. It has one and two columns. So this is a 2 by 2. So we can be able to add this element wise, and to add the tensor, it's just very easy. it's more or less taking the first element in the first tensor, and you add to the first element in the second tensor. Like we can take 1 plus 5 is 6, and we have our tensor here 6. We have we have 2. We go to the second element in the first row of each tensor, and we have 2 plus 6 is 8, and that is the addition for the first tensor that we have here. Then for the second one, it's pretty much the same way. You take the element, and this is going to be another tensor here that we are creating, but you take the element here is 3 plus 7 is 10, and 4 plus 8 is 12. So, and that's the second one there. And this tensor, obviously, you can see it's 1 row, 2 rows, and 1 column, 2 columns. So it's 2 by 2. See, these are the rows. That's 1 row. And this is another row here. That's another row. Is the comma there separating the rows. So this is 1 row, 2 rows. So that's 2. And then the columns is the 6 is the first column. The 8 is the second column. And 10 is the first column and in the second row. And 12 is the second column in the second row. So this tensor is a 2 by 2. 2 rows, 2 columns. Remember, rows, columns. Rows and columns. And then we go to the next one. That's how you can do element-wise addition. And this for tensors. And this works, for this to work, both tensors that you are adding should have the same shape. 2 by 2, 2 by 2. That's addable. We go next here and we talk a little bit of a concept about broadcasting and how we can be able to broadcast the shape of a tensor during addition. And I've written here, broadcasting is a powerful mechanism that lets PyTorch perform arithmetic operations on tensors of different shapes. Again, we said shape, very important concept. We'll see this even as we go deeper into machine learning and working with models and all that. So shapes, very important. The shape of a tensor, very, very important. When we are broadcasting, we say that the smaller tensor is broadcast across the larger tensor so that they have compatible shapes. And broadcasting follows some rules. Rule number 1 is that if the tensors have a different number of dimensions, remember we had the 0-dimension tensor, which was the scalar. We had the 1-dimension tensor, which was the vector. Then we have the 2-dimension tensor, which is the matrix, and 3-dimension, so on like that. So if the tensors have a different number of dimensions, prepend the shape of the smaller tensor with 1s until both shapes have the same length. Number 2, the 2 tensors are compatible in a dimension if they have the same size in the dimension, or if one of the tensors has a size 1 in that dimension. And number 3 rule is that the tensors can be expanded without copying data to fill the shape resultant from the above rules. So say that we have a tensor of size 1, 2, and we want to add it to a tensor of size 2, 2. Like for instance, we have a tensor 3 here, which is of size, remember the size of a tensor is the rows, and this is just 1 row. So you can see this is one row here. And then columns, the columns you can see is one column and another column where the 200 is. So the first column is where the 100 is, the second column is where the 200 is, and this is row, one row. The rows are horizontal, the columns are the vertical. So this is one row and two columns. So this is shape 1, 2. And we have another tensor. Say we have a tensor of shape. We have how many rows? We have one row, comma, and then we have another row, comma. So this is a 2 by columns 1, 2. Columns 1 where 3 is and 2 where 4 is. So this is a tensor of shape 2, 2. So suppose you now wanted to have these two tensors, which are obviously of different sizes, tensor 3, and which is of size or rather of shape 1, 2, and tensor 1, which is of shape 2, 2. The way you do it is that you actually work by broadcasting. We take tensor 3 and we broadcast because it's the smaller tensor. So we take tensor 3 and we broadcast tensor 3. We broadcast to the shape of tensor 1 during the addition. So for instance, we're gonna take, tensor 3 as only one row but two columns. So we're gonna broadcast the two columns to each of the columns in the second tensor, which has two rows. So we're gonna take this first column, which is 100, then we're gonna go to the second tensor and add this to the first column in the first row of the second tensor. So we're going to take this 100 plus 1, which will give us 100. Then we also broadcast this 100 to the first column of the second row, which is going to be 100 broadcast to 3. That's going to be, it's going to be 103. And this is the second row. This is in the second row. The first column in the second row. So it's gonna come here, and we have the 103. And we do the same thing for the second column. So we broadcast this 200 to the second column in the first row of the second tensor. So we take this 200, broadcast it here, we get 202. So that 202 comes here. And then we also do the same thing. We take the second column and we broadcast it to the second column in the second row. This is going to be 200 plus 4, which is going to give us 204. And the shape is going to be 2 by 2. Shape is going to be 2 by 2. It's going to be the one of the size of the one of the bigger tensor. So 2 by 2 is going to be the shape. You see, we have 2 rows and 2 rows and 2 columns. So it's 2 by 2. But that's how you broadcast. You take the first, in our case here, because we have one row, we take the first column in that one row, then we broadcast that first column to the first column in the first row of our second tensor. So we take 100 plus 1, and then we also broadcast this first column. We broadcast it to the first column of the second row, because the other tensor has 2 rows, and so we broadcast this to 200 plus 3, and oh, I mean 100, sorry, 100 plus 3, and that's going to give us the 103 here. And then we do the same thing for the second column, 200, but this time we go to the second column and second row. So 200 plus 2, we have 202, and then we do the same thing, second column in the first tensor, then in the second tensor we go to the second row and second column, which is going to give us 204. And that's how we do the broadcasting. We'll see this as we go as well, but most of the time these calculations are normally done by machines, so we won't really get into the deep about calculations and operations, but it's something that it's very helpful at least to be aware of. And well, talking about that, practical use cases. So this can be used in updating weights in neural networks like the addition and operator. It can be used in updating weights in neural networks because during training of our models, updates to the weights of the neural network are performed by adding gradients multiplied by a negative learning rate to the weight tensor. Don't worry about this, but just understand that there is actually an application, there is a practical use case for these tensor operations. The only thing is that this is normally done by the neural network automatically, and we really don't need to do the calculations, but it's just good to know. It can also be used, the addition can also be used in aggregating data, when combining data from multiple tensors, such as summing up different feature maps in CNN neural network. And I will go to the next because I really want to go a little bit faster. Subtraction is pretty much the same way. We subtract like 4 minus 1, we have 3. Then 8 minus 2, we have 6. Then 12 minus 3, we have 9. Then 16 minus 4, we have 12. So subtraction. And again, the shape should be the same. If you are doing element-wise subtraction, this is a shape 2 by 2, 2 by 2. And the resultant shape is also going to be 2 by 2. 2 rows and 2 columns, 2 by 2. So we go next to subtraction broadcasting. Same rules as we did with addition. We have a tensor 4, 6, which is of shape 1 row, 2 columns, so 1, 2. And we also have another tensor 1, which is of size 1 row, 2 rows, 1 column, 2 column, 1 column, 2 columns. It's size 2, 2. So to subtract with broadcast, we do the same thing that we did. We take the first one here, the first column, then we broadcast it. So this is going to be first column, and we go to the second tensor, and we go to the first row, first column, and we take this minus 4 is 0, and that's going to be right here. Then we do the same thing here. We take the first column, and we also go to the first column in the second row. 4 minus 12 is negative 8. So it's negative 8, but the way I'm doing it is actually here with the result of the broadcast is actually tensor 1 minus tensor 3. So we are doing it the other way around. We are having so this, instead of being negative, it's going to be positive because we are doing it from tensor 1. So it's like we are taking 12 minus 4, which is 8. And then for the same thing, we come here to 6, we broadcast it. and this is the second. The second column in our first tensor. And so we have 6, and then we go to the second one. But this is going to be like 6 minus 8, which, as we said, because we are working from tensor 1 minus tensor 3, it's going to be 8 minus 6, which we have 2 here. And then the same thing, second column in the first tensor, and second column in the second row in the second tensor. So it's 16 minus 6, which is 10 here. So same concepts, pretty much broadcasting, as we have seen with addition. Also a very important concept to understand. If it was tensor 3 minus tensor 1, then we would have the negatives. But for now, I think it kind of like makes a lot of sense. The shape of the tensor is rows 1, 2, and columns 1, 2. So it's 2 by 2. We go to the next one. Practical uses for subtraction would be loss computation in many machine learning tasks, especially regression. The difference between predicted values and actual values, that's the targets, is computed using tensor subtraction. This difference often forms the basis of loss function. Loss functions like mean squared error and other loss functions. And also for model error analysis, subtracting one tensor predicted values from another actual values can help in analyzing the errors made during a model, meant by a model, helping in debugging and also improving the model. So the point is, these applications for these subtractions, these arithmetic operations that we are learning about, it's only that for the most part, this will be done. We'll do it in a computer sense. So we won't really do like mathematics itself, but it's going to be inbuilt in the computer code that we will be writing. And then next, I wanted to talk about multiplication. A little bit complex, but I'll just run over it a little bit because I want to really see whether we can finish this in this video before it gets too long. So tensor multiplication in PyTorch is a fundamental operation that can be performed in several ways depending on the context of the specific needs of the tasks. So there's different types of tensor multiplications available in PyTorch, including element-wise multiplication, matrix multiplication, and also batch matrix multiplication. And each serves different purposes in data processing and also in neural network computations. And they're different, as you will see. We'll go next here. Element-wise multiplication, pretty simple. Again, remember, the shape has to be the same. The shape has to be the same. These are 2 by 2 tensor. These are 2 by 2 tensor. So we multiply the same way. 1 times 5 is 5. 2 times 6 is 12. 3 times 7 is 21. 4 times 8 is 32. So pretty easy. Resultant shape, also same as the tensors. They are both of the same shapes, and it's going to be 2 by 2. 2 rows and 2 columns. So we go to matrix multiplication, and this is where I want to kind of like spend a little bit of time, so at least you can be able to kind of like see what's happening, because it can seem to be a little bit confusing, but once you get the hang of it, it's actually very easy, very easy. It's more about, remember, our rows and columns, rows and columns, rows and columns. And as long as you remember our rows and columns, everything really works pretty good. But there are some rules, and I want to talk to you about those as we go. But anyway, matrix multiplication in PyTorch is performed using torch.matmul function, which is a multiplication, matrix multiplication, torch.matmul, and a function, or the at at operator, at like when you say at gmail.com, at operator. So this type of multiplication is crucial for operations involving transformations of data in neural networks, such as passing data through layers. So it's very important. We won't be able to do it really when we are writing our models, but this is what part of what our models are going to be doing as they learn, as they pass data through the layers. And so it's just good to have an idea of what's really happening. There's a lot of mathematics happening, and some of this mathematics involves matrix multiplication, and it normally requires inner dimensions of the two matrices or tensors to match. This is very important. And you can tell whether you can be able to matrix multiply a tensor with another tensor depending on the shape of the tensor. The shape of the tensor, very important. It requires the inner dimensions of the two matrices or tensors to match. We have, for instance, remember, inner dimensions of the two matrices to match. Like for instance, we have this tensor here called matrix 1, and it is of shape, it's one row. We have one row here. So it's a one row by how many columns? We have 1, 2, 3 columns. So this is 1 by 3. And then we also have another matrix here of shape. How many rows? We have 1, 2, 3 rows. And how many columns? So it's 3. How many columns we have? We have 1 column here. Then we have another column. We have 1 column here and another column here. We have 1 column here and another column here. We have 1 column here and another column here. So the column is 2. So this is 3 rows, 1 row where the square brackets are. This is 1 row up to there. Then there's another row here up to here. Then there's another row here up to here. So that's 3 rows, 3, and there's 1 column, comma, another column. 1 column, comma, another column. 1 column, comma, another column. So the columns are 2. So 3 by 2. So this rule here, it requires the inner dimensions of the two matrices or tensors to match. It's very important, and it's actually what is going to determine whether you can be able to matrix multiply two tensors. The inner dimension for this is the 3, and the inner dimension for this is the 3. So if you are multiplying matrix 1 by matrix 2, if matrix 1, the inner dimension is a 3, then the other inner dimension of the other tensor you are multiplying should be a 3. So if this is a 3, this should be a 3. If this is a 5, this should be a 5. If this is a 7, this should be a 7. If this is a 10, this should be a 10. If this is 20, this should be 20. So these two must match. Otherwise, you'll get a runtime error because you cannot matrix multiply if those inner dimensions of the two matrices do not match, of the two tensors do not match. The inner dimensions have to match for you to be able to matrix multiply. And funny thing is that if you multiply matrix 1 and matrix 2, we saw the inner dimensions, the 3 and 3 have to match. But the funny thing is that the resulting shape of the new tensor once you multiply is going to be of type, or rather of the resulting shape is going to be of the other items that you have in that tensor. So like when we multiply matrix 1 and matrix 2, the shape of the resulting multiplied matrix is going to be of type 1, 2. 1, 2. So it's interesting, but you can always tell the shape of the resulting matrix by, once you take the inner dimensions out, then it's going to be these ones on the outer. The outer ones are going to determine the shape. and it's very interesting. But so let's see how we can matrix multiply this tensor. Matrix multiplication is pretty much very easy, especially once you get a hold of it or the hang of it. It's pretty much taking the column and then you run the columns through the rows, and then you do summation, and that is gonna give you it's gonna give you the product. For instance, we have this matrix, matrix 1, which is of a shape 1 row 3 columns 1 3, and we have this matrix 2, which is of shape 1 2 3 rows 1 2 2 columns 3 2. So we have these two matrices. To multiply this matrix, essentially what you do is that you take the first column, then you run that through the rows, through the first row, and then to multiply the this matrix 2 tensor is, it has 2 columns, so we still take that column and we go to the second column and multiply it like that for each row. You go to the second column for each row in the second matrix and multiply it. So we will, and then add them together, and then you have your summation and finally your multiplication. So we take this 3 times this 2, which is 6, and then we go to 1 times 1, which is 1. So we have 6 plus 1, which is 7. And then we go to 4 times 2, which is 8. And 8 plus 7 is 15. So that is our first number for the multiplication. And then we do the same thing for the second column in matrix 2. We go to 3 times 0, which is 0. Then we go to 1 times 2, which is 2. So 2 plus 0 is 2. And then we go to 4 times 5, which is 20. And 20 plus 2 is 22. And there we have it. We have 15 to this tensor, this multiplication. It's the product of the multiplication of matrix 1 and matrix 2. And as we said, the shape is going to be 1 2. See this 1 2. And the shape of our final multiplication tensor is 1 2. 1 row 2 columns 1 2. So that's how we do matrix multiplication. It's pretty easy once you get a hang of it, but when the matrix are a little bit bigger, it can become a little bit complicated. If you want me to do another video primarily on matrix multiplication, let me know in the comment section. But once you practice it and you go actually online, there is some websites that let you do matrix multiplication, and you can see how the columns are multiplied by the rows and then added over, and it's pretty neat. When we are doing our machine learning and designing our models, this is the multiplication just as with the addition and the subtraction. These are going to be done by the computer, but it's always good to know what's going on. We also have another matrix multiplication with a batch matrix multiplication, which allows you to multiply batches of matrices together. It is particularly useful in neural networks where you deal with batches of input data, and each item in the batch is a matrix to be multiplied, and this operation is supported by torch.bmm function. The batch dimensions must be the same, and the matrices weight within must comply with the usual matrix multiplication rules. I'll let you look through this, and maybe if you are interested, you can go online and try to see about this. But for the most part, I just wanted you to introduce you to basic tensor operators and show you about basic tensor operations. And we'll continue to see this as we go, but most of the time this, as I said, is going to be done essentially by the computer. So we won't be doing a lot of mathematics. What we are going to be doing is a lot of coding, and that is what I want to be a little bit more focused on. So I will go to the next. We have tensor operations with division, and we can do element-wise division, which works similar to multiplication, to subtraction that we have seen before. So for instance, to divide tensor 1 by tensor 2, you take element-wise, one element at a time. 1 divided by 5, you get 0.20, and 2 divided by 6, and so on and so on. So pretty much that's how we do these operations. Nothing really that fancy. Most important thing is you can get from this is that the shape of the tensor is very important, as we have seen with matrix multiplication. We cannot be able to perform matrix multiplication if the inner dimensions of the tensors do not match. And this is where a lot of errors, once we start building machine learning models, this is where a lot of errors can also come from. So we will be able to make sure that those shapes can be multiplied, matrix multiplied. So it's very important one day to introduce you to a little bit of this, so you can be able to at least have a little bit of familiarization with tensors and also with tensor operations. And it was very nice actually talking about tensors, and I look forward to us actually working, programming, coding with tensors. I'm gonna check out for now. Love is free. Subscribe, and much love to the world. Thank you, guys.